Close your eyes for a moment and let yourself drift. Imagine floating in the endless expanse of space, where the stars are not just points of light, but ancient storytellers, whispering secrets of the cosmos. Around you, the universe stretches in every direction, vast and silent, yet alive with mysteries waiting to be unraveled. And there, hidden in the shadows of the night sky, lies one of the greatest enigmas of all, a sphere so immense, so invisible, that it defies everything we think we know about the universe. This is the Galactic Halo, a ghostly cloak of dark matter that wraps itself around galaxies, shaping their destiny while remaining forever unseen. Tonight, we embark on a journey to uncover the secrets of this cosmic phantom, to explore the invisible threads that bind the universe together. So, wherever you are, whatever time it is, let yourself be carried away by the wonder of the unknown, because out there, in the quiet darkness, the galactic halo waits, holding answers to questions we have yet to ask. Now, let us turn our gaze to the heart of this cosmic mystery, the galactic halo itself. Picture a vast, invisible sphere surrounding a galaxy, like an unseen guardian holding everything together. This is the galactic halo, a structure made almost entirely of dark matter, stretching far beyond the visible edges of galaxies. While we cannot see it directly, its presence is undeniable, shaping the very fabric of the universe. The galactic halo plays a crucial role in the structure and behavior of galaxies. Without it, galaxies as we know them would not exist. It acts like an invisible scaffold, providing the gravitational glue that keeps stars, gas, and dust from flying apart. Imagine a spinning top. Without its weight and balance, it would wobble and fall. In the same way, the galactic halo's gravitational pull stabilizes galaxies, allowing them to rotate and maintain their shape over billions of years. But here's the twist. The galactic halo is invisible. It doesn't emit, reflect, or absorb light, making it impossible to detect with traditional telescopes. Yet, its influence is everywhere. Astronomers first began to suspect its existence when they noticed something strange: galaxies were spinning faster than they should, given the amount of visible matter they contain. This discrepancy led to the realization that there must be something more, something unseen, exerting a gravitational force. That something is dark matter, the mysterious substance that makes up the galactic halo. This invisible force is not just a passive observer, it actively shapes the universe. The galactic halo's gravitational pull affects the motion of stars within galaxies, the formation of new stars, and even the paths of entire galaxies as they move through space. It's like a cosmic puppeteer, pulling strings we can't see, but whose effects are written across the night sky. And yet, for all its influence, the galactic halo remains one of the greatest puzzles in modern astronomy. How can something so massive, so fundamental to the structure of the universe, remain hidden from our view? This question lies at the heart of the mystery, drawing scientists and dreamers alike into the quest to understand the invisible forces that shape our cosmos. As we continue this journey, we'll explore how scientists first began to uncover the secrets of the galactic halo, the tools they used to study it, and the questions that still linger in the shadows of the unknown. For now, let this thought linger somewhere out there. In the vast expanse of space, the galactic halo waits, a silent enigma holding the keys to understanding the universe itself. Now, let's take a closer look at the invisible force that defines the galactic halo, dark matter. Imagine you're in a room filled with invisible furniture. You can't see it, but every time you try to walk across the room, you bump into something. That's dark matter. It's everywhere, shaping the universe, yet it remains completely hidden from our eyes. Dark matter is unlike anything we encounter in our everyday lives. Ordinary matter, the stuff that makes up stars, planets, and even our own bodies, interacts with light. It reflects, absorbs, and emits it, allowing us to see and study it. Dark matter, on the other hand, doesn't play by these rules. It doesn't interact with light at all, which is why it's invisible. Think of it as a ghostly presence, passing through walls and objects without leaving a trace. But just because we can't see dark matter doesn't mean it's not there. In fact, it makes up about 85% of all matter in the universe. That means the stars, planets, and galaxies we see are just the tip of the cosmic iceberg. The rest is dark matter, silently shaping the cosmos. So, how do we know it exists? The answer lies in its gravitational effects. Dark matter may not interact with light, but it does interact with gravity. Picture a merry-go-round spinning faster than it should, as if an unseen hand were pushing it. That's what happens with galaxies. They rotate at speeds that can't be explained by the visible matter alone. The only explanation is that something invisible, dark matter, is providing the extra gravitational pull. Detecting dark matter is one of the biggest challenges in modern science. Since it doesn't emit or absorb light, traditional telescopes are useless. Instead, scientists rely on indirect methods, like observing how its gravity bends light from distant objects, a phenomenon called gravitational lensing. It's like trying to find a shadow in a dark room by watching how it distorts the light around it. Despite its elusive nature, dark matter is essential to our understanding of the universe. Without it, galaxies wouldn't have enough gravity to hold themselves together, and the cosmos as we know it wouldn't exist. It's the unseen architect, quietly building and maintaining the structures that fill the night sky. As we move forward, we'll explore how scientists first began to piece together the puzzle of dark matter and the groundbreaking tools they've developed to study this invisible force. For now, let this thought sink in somewhere out there. In the vast expanse of space, dark matter is at work, shaping the universe in ways we're only beginning to understand. Now, let's step back in time to uncover how the mystery of the galactic halo first began to unfold. The story of its discovery is a testament to human curiosity and the relentless pursuit of understanding the cosmos. It all started in the early 20th century, when astronomers began to notice something peculiar about the way galaxies behaved. One of the key figures in this discovery was Fritz Zwicky, a Swiss astronomer working in the United States. In the 1930s, Zwicky was studying the Coma Cluster, a massive group of galaxies. He noticed that the galaxies within the cluster were moving much faster than expected. Based on the visible matter alone, the cluster shouldn't have had enough gravity to hold itself together. Zwicky proposed that there must be some unseen matter, what he called dunkel materie, or dark matter, providing the extra gravitational pull. Around the same time, another astronomer named Jan Uwit was studying the motion of stars in our own Milky Way. He observed that stars near the edge of the galaxy were moving faster than predicted by the visible mass. Like Zwicky, Uwit suggested that there must be some invisible material influencing their motion. These early observations laid the groundwork for the concept of the galactic halo, a vast sphere of dark matter surrounding galaxies. However, proving the existence of dark matter and the galactic halo was no easy task. For decades, the idea remained controversial. Many scientists were skeptical, arguing that the observations could be explained by other factors, such as errors in measurements or unknown properties of gravity. It wasn't until the 1970s that the evidence became too compelling to ignore. Vera Rubin, an American astronomer, played a pivotal role in solidifying the case for dark matter. She studied the rotation curves of galaxies, measuring how fast stars orbited their centers at different distances. Rubin found that stars on the outer edges of galaxies were moving just as fast as those near the center, defying the laws of gravity as they were understood at the time. Her work provided some of the strongest evidence yet for the presence of dark matter in the galactic halo. Despite these breakthroughs, the challenges didn't end there. Detecting something invisible required entirely new approaches. Scientists had to rely on indirect methods, such as gravitational lensing and the study of cosmic microwave background radiation, to map the distribution of dark matter. Each step forward brought new questions, but also new tools to explore the unseen. The discovery of the galactic halo is a story of persistence and ingenuity. It reminds us that the universe often hides its secrets in plain sight, waiting for the right tools and minds to uncover them. As we continue our journey, we'll explore how modern science is pushing the boundaries of what we know about this invisible force and its role in shaping the cosmos. Now, let's turn our attention to the ingenious tools and techniques scientists use to map the invisible. Studying something as elusive as the galactic halo requires creativity and cutting-edge technology. One of the most powerful methods is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant object, like a galaxy, passes near a massive object, such as a cluster of galaxies, the gravity of the massive object bends the light, acting like a cosmic magnifying glass. This bending can reveal the presence of dark matter in the galactic halo, as it distorts the images of background objects in ways that can be measured and analyzed. Another crucial tool is the study of the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. This ancient light carries imprints of the early universe, including the distribution of dark matter. By analyzing tiny fluctuations in the CMB, scientists can map the large-scale structure of the universe and infer the presence of dark matter in the galactic halo. These observations provide a snapshot of how dark matter has shaped the cosmos over billions of years. In addition to these methods, astronomers use computer simulations to model the behavior of dark matter. By inputting known physical laws and initial conditions, these simulations predict how dark matter should clump together and form structures like the galactic halo. Comparing these predictions with real-world observations helps refine our understanding of dark matter's properties and distribution. Each of these techniques has its strengths and limitations, but together they form a powerful toolkit for exploring the unseen. Gravitational lensing offers a direct way to see dark matter's effects, while the CMB provides a historical record of its influence. Simulations, on the other hand, allow scientists to test theories and make predictions about dark matter's behavior. As we continue to refine these tools and develop new ones, the mystery of the galactic halo becomes a little less mysterious. Each discovery brings us closer to understanding the invisible force that shapes our universe. And with that, we're ready to explore another fascinating aspect of this cosmic enigma, the spherical nature of the galactic halo and why its shape holds such significance. Now, let's take a closer look at the shape of the galactic halo itself, a sphere of mystery that holds the key to understanding dark matter's role in the cosmos. Unlike the flat, disk-like structure of a galaxy's visible stars and gas, the galactic halo is spherical, enveloping the galaxy in an invisible cocoon. This shape is no accident. It's a direct result of dark matter's unique properties. Unlike ordinary matter, which clumps together to form stars, planets, and galaxies, dark matter doesn't interact with light or other forms of electromagnetic radiation. Instead, it spreads out evenly, creating a vast, spherical cloud that extends far beyond the visible edges of a galaxy. The spherical shape of the galactic halo is significant because it reveals how dark matter behaves on a cosmic scale. While visible matter collapses into flat disks due to gravity and rotation, dark matter remains diffuse, forming a halo that surrounds and supports the galaxy. This halo acts like a scaffold, providing the gravitational framework that holds galaxies together. Without it, galaxies like our Milky Way would fly apart, their stars scattering into the void. The spherical nature of the halo also explains why dark matter's influence is felt so uniformly across a galaxy, shaping its structure and guiding its evolution. But why a sphere? The answer lies in the way dark matter interacts, or rather, doesn't interact, with the forces that shape ordinary matter. Dark matter particles don't collide or stick together like atoms do. Instead, they pass through each other, creating a smooth, even distribution. Over billions of years, this distribution settles into a spherical shape, influenced only by gravity. This is why the galactic halo doesn't have the intricate spiral arms or dense cores we see in visible galaxies. It's a simpler, more fundamental structure, yet one that plays a crucial role in the universe's architecture. The spherical shape of the galactic halo also sets it apart from other galactic structures, like the flattened disks of spiral galaxies or the irregular shapes of dwarf galaxies. While these visible structures are dynamic and ever-changing, the halo remains stable and unchanging, a silent guardian of the galaxy. Its spherical form is a testament to the simplicity and elegance of dark matter's influence, a reminder that even the unseen can shape the cosmos in profound ways. As we continue to explore the galactic halo, its spherical nature offers a glimpse into the hidden forces that govern the universe. It's a shape that speaks to the mystery and majesty of dark matter, a cosmic enigma that continues to challenge and inspire us. And with that, we're ready to delve deeper into how this invisible sphere played a pivotal role in the formation of galaxies, shaping the universe as we know it. Now, let's turn our attention to the role dark matter plays in the very birth and growth of galaxies. The galactic halo, with its vast, invisible presence, has been a silent architect in shaping the universe as we know it. Long before the first stars ignited, dark matter was already at work, laying the foundation for galaxies to form. Its gravitational pull acted like a cosmic glue, gathering clouds of gas and dust into dense regions. Over time, these regions grew denser, eventually collapsing under their own gravity to form the first stars and galaxies. Dark matter's influence didn't stop there. As galaxies began to take shape, the halo's gravitational force continued to guide their evolution. Imagine the galactic halo as an invisible hand, gently sculpting the structure of a galaxy. It provided the gravitational framework that allowed stars to form and cluster together, creating the intricate patterns we see in spiral galaxies like the Milky Way. Without dark matter's steady pull, galaxies would lack the stability needed to hold their shape, and the universe would look very different. One of the most fascinating aspects of dark matter's role is its impact on star formation. While ordinary matter clumps together to form stars, it's the gravitational influence of dark matter that creates the conditions for this process to occur. The halo's gravity pulls gas and dust into dense regions, where they can cool and collapse, eventually igniting into stars. This process is ongoing, with dark matter continuing to shape the birth of new stars even today. In fact, the Milky Way's spiral arms, where star formation is most active, owe their existence to the gravitational scaffolding provided by the galactic halo. But dark matter's role isn't just about creating stars, it's also about sustaining them. The halo's gravitational pull helps maintain the delicate balance within a galaxy, ensuring that stars and gas remain bound together rather than drifting apart. This balance is crucial for the long-term survival of galaxies, allowing them to grow and evolve over billions of years. Without dark matter, galaxies would lack the gravitational strength to hold onto their stars, leading to a universe filled with scattered, isolated stars rather than the vibrant galaxies we see today. As we reflect on dark matter's role in galaxy formation, it's clear that this invisible force has been a driving factor in the universe's evolution. From the first flickers of starlight to the majestic spirals of galaxies like the Milky Way, dark matter has shaped the cosmos in ways we are only beginning to understand. And as we continue to explore its mysteries, we uncover more about the hidden forces that have shaped our universe from its earliest moments. With this in mind, let's now explore how dark matter's presence led scientists to confront one of the greatest puzzles in astrophysics, the missing mass problem. Now, let's shift our focus to one of the most intriguing puzzles in astrophysics, the missing mass problem. For decades, scientists observed that the visible matter in galaxies, like stars and gas, simply didn't account for the gravitational forces at play. Galaxies were spinning faster than they should have been, and their outer regions were behaving in ways that defied the laws of physics as we understood them. Something was missing, and that something was mass, a lot of it. This discrepancy became known as the missing mass problem, and it left astronomers scratching their heads for years. The solution to this cosmic mystery came in the form of dark matter, and the galactic halo played a key role in unraveling it. When scientists calculated the gravitational pull needed to explain the motion of stars and gas within galaxies, they realized that the visible matter alone couldn't provide enough force. There had to be something else, something invisible, exerting a gravitational influence. This is where the galactic halo stepped in. Its vast, spherical structure, composed of dark matter, provided the missing mass needed to balance the equations. The halo's gravitational pull explained why galaxies didn't fly apart and why their outer regions moved the way they did. But how did scientists connect the dots? One of the most compelling pieces of evidence came from studying the rotation curves of galaxies. These curves map how fast stars and gas move at different distances from a galaxy's center. In a universe governed only by visible matter, stars on the outer edges of a galaxy should move slower than those closer to the center. But observations showed the opposite. Stars on the outskirts were moving just as fast, if not faster. This could only mean one thing. There was an invisible source of mass spread throughout the galaxy, providing the extra gravitational pull needed to keep everything in place. That invisible source was the galactic halo. The discovery of the galactic halo didn't just solve the missing mass problem, it reshaped our understanding of the universe. It showed us that what we see is only a fraction of what's out there. Dark matter, though invisible, makes up the majority of a galaxy's mass, and the galactic halo is its most prominent manifestation. Without this hidden structure, galaxies as we know them wouldn't exist. They would lack the gravitational scaffolding needed to hold their shape and sustain their motion. As we continue to explore the mysteries of the galactic halo, we gain deeper insights into the forces that govern the cosmos. The missing mass problem was just the beginning, a clue that led us to uncover the invisible hand shaping the universe. And with that, let's now turn our attention to how scientists use computer simulations to model the behavior of the galactic halo, bringing this invisible structure to life in ways we can study and understand. Now, let's step into the digital realm, where scientists use the power of computer simulations to bring the invisible galactic halo to life. Imagine trying to study something you can't see, touch, or directly measure. That's the challenge astronomers face with dark matter and the galactic halo. But thanks to advanced technology, they've found a way to simulate this mysterious structure, allowing them to explore its behavior and influence on the universe. Computer simulations start with the laws of physics, gravity, motion, and the interactions between particles. Scientists input what they know about dark matter, such as its gravitational effects, and then let the simulation run. These virtual models create a dynamic, three-dimensional representation of the galactic halo, showing how it interacts with galaxies, bends light, and shapes the cosmos over billions of years. It's like building a cosmic sandbox where researchers can test theories and observe outcomes in real time. One of the biggest challenges in simulating the galactic halo is its invisibility. Since dark matter doesn't emit light or interact with electromagnetic forces, scientists have to rely on indirect clues to guide their models. They use observations of galaxy rotation curves, gravitational lensing, and the distribution of visible matter to fine-tune their simulations. Even then, there's a lot of guesswork involved. The properties of dark matter, its density, temperature, and how it clumps together, are still largely unknown, making it difficult to create a perfect model. Despite these challenges, simulations have been incredibly revealing. They've shown how the galactic halo acts as a gravitational scaffold, holding galaxies together and influencing their formation. They've also helped scientists predict how dark matter behaves in extreme environments, like during galaxy collisions or near supermassive black holes. These virtual experiments have become essential tools for understanding the invisible forces shaping our universe. But simulations aren't just about solving mysteries, they're also about sparking new questions. Every time a simulation reveals something unexpected, it pushes scientists to rethink their assumptions and explore new possibilities. It's a constant cycle of discovery, where each virtual experiment brings us closer to unraveling the secrets of the galactic halo. As we continue to refine these simulations, we're not just studying dark matter, we're building a bridge between the seen and the unseen, the known and the unknown. And with that, let's now explore the leading candidates for dark matter particles, the elusive building blocks that make up the galactic halo. Now, let's turn our attention to the building blocks of the galactic halo itself, the particles that might make up dark matter. Among the leading candidates are weakly interacting massive particles, often called WIMP, and axions. These particles are at the heart of the mystery, and understanding them could unlock the secrets of the invisible universe. WIMP are hypothetical particles that, as their name suggests, interact very weakly with ordinary matter. They're thought to be massive compared to other subatomic particles, which would explain why dark matter has such a strong gravitational influence. Despite their size, WIMP are incredibly elusive. They don't emit light, absorb it, or interact with electromagnetic forces, making them nearly impossible to detect directly. Scientists believe they might occasionally collide with atomic nuclei, but even these rare interactions are so faint that they're extremely difficult to observe. On the other hand, axions are another promising candidate. Unlike WIMP, axions are theorized to be extremely light particles, almost ghost-like in their nature. They were originally proposed to solve a problem in particle physics, unrelated to dark matter, but researchers soon realized they could also explain the missing mass in the universe. Axions are thought to interact even more weakly than WIMP, making them even harder to detect. However, their low mass and unique properties mean they could behave differently in certain conditions, offering a new way to search for them. What makes both WIMP and axions so challenging to study is their lack of interaction with the forces we're familiar with. They don't produce light, heat, or any other detectable signals, which means scientists have to get creative. Experiments often involve highly sensitive detectors placed deep underground to shield them from cosmic interference. These detectors are designed to catch the faintest hints of dark matter particles, whether it's a rare collision with a WIMP or the subtle conversion of an axion into a photon. Despite decades of searching, neither WIMP nor axions have been definitively detected. This doesn't mean they don't exist. It simply highlights how elusive they are. The search for these particles is like trying to find a needle in a cosmic haystack, where the needle is invisible and the haystack is the entire universe. Yet, every experiment brings us closer to understanding whether these particles are the key to dark matter, or if the answer lies elsewhere. As we continue to explore these possibilities, one thing is clear. The search for dark matter particles is not just about solving a scientific puzzle. It's about uncovering the fundamental nature of the universe itself. And with that, let's now delve into the experiments conducted deep underground, where scientists are hunting for these elusive particles in some of the most extreme environments on Earth. Now, let's take a closer look at where the hunt for dark matter particles unfolds. Deep beneath the Earth's surface, underground experiments are at the forefront of this search, offering scientists a unique environment to detect the faintest signals of these elusive particles. But why go underground? The answer lies in the need to shield these sensitive experiments from the constant bombardment of cosmic rays and other background noise that could interfere with the results. One of the most famous facilities for such experiments is the Large Hadron Collider, located beneath the border of France and Switzerland. While the collider is best known for its role in discovering the Higgs boson, it's also a key player in the search for dark matter. By smashing particles together at incredibly high speeds, scientists hope to create conditions that might reveal the presence of dark matter particles, such as WIMP or axions. These collisions could produce traces of dark matter, even if only for a fleeting moment, providing clues about their properties. But the Large Hadron Collider isn't the only place where this search is happening. Deep underground laboratories, like the one in Sudbury, Canada, or the Gran Sasso National Laboratory in Italy, are also critical to the effort. These facilities are often located in old mines or beneath mountains, where layers of rock act as a natural shield against cosmic interference. This isolation allows detectors to focus on the faint signals that might indicate the presence of dark matter particles. One of the most intriguing experiments is the use of liquid xenon detectors. These devices are filled with ultra-pure xenon, a noble gas that emits tiny flashes of light when a particle interacts with it. If a WIMP were to collide with a xenon atom, it would produce a faint signal that scientists could potentially detect. Similarly, experiments searching for axions use powerful magnetic fields to try and convert these ghostly particles into detectable photons. These methods are incredibly sensitive, requiring extreme precision and care to avoid contamination or interference. The challenges of these experiments are immense. Detectors must operate at extremely low temperatures, often just a fraction of a degree above absolute zero, to minimize noise. Even the smallest vibrations or temperature fluctuations could disrupt the results. Yet, despite these difficulties, scientists remain hopeful. Every experiment, whether it succeeds or not, brings us closer to understanding the nature of dark matter. As we continue to explore these underground laboratories, it's clear that the search for dark matter is as much about innovation as it is about discovery. The tools and techniques being developed today could revolutionize our understanding of the universe, revealing not just the secrets of dark matter, but also opening new doors to the fundamental laws of physics. And with that, let's now turn our attention to another fascinating clue in the dark matter mystery: gravitational lensing, and how it helps us map the invisible. Now, let's shift our gaze to the skies, where another remarkable tool helps us uncover the secrets of the galactic halo: gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when massive objects, like galaxies or clusters of galaxies, bend the light from objects behind them. Imagine it as a cosmic magnifying glass, where the immense gravity of a massive object warps the fabric of space-time, distorting and amplifying the light from distant stars or galaxies. This bending of light not only creates stunning visual effects, but also provides crucial clues about the presence and distribution of dark matter in the galactic halo. One of the most striking examples of gravitational lensing is the Einstein cross, a quasar whose light is split into 4 distinct images by the gravitational influence of a foreground galaxy. This cosmic alignment allows astronomers to study the properties of both the distant quasar and the galaxy, acting as the lens. But more importantly, it reveals the presence of dark matter. The way the light bends tells us that there's more mass in the lensing galaxy than what we can see, mass that must be attributed to dark matter. Another fascinating example is the bullet cluster, a pair of colliding galaxy clusters. Observations of this system show that the visible matter, like gas and stars, interacts and slows down during the collision, while the dark matter, detected through gravitational lensing, passes through unaffected. This separation between visible and dark matter provides some of the strongest evidence for the existence of dark matter and its role in shaping the galactic halo. Gravitational lensing also helps us map the distribution of dark matter on a larger scale. By studying how light from distant galaxies is distorted as it passes through the galactic halo, scientists can create detailed maps of where dark matter is concentrated. These maps reveal that dark matter isn't evenly spread out, but forms a web-like structure, with dense clumps and filaments connecting galaxies across the universe. This cosmic web, woven by dark matter, plays a crucial role in the formation and evolution of galaxies, including our own Milky Way. The beauty of gravitational lensing lies in its ability to reveal the invisible. It allows us to see the unseen, to map the unobservable, and to piece together the puzzle of the galactic halo. Each lensed image, each distorted galaxy, is a clue that brings us closer to understanding the nature of dark matter and its profound influence on the cosmos. And as we continue to explore these cosmic clues, we're reminded that the universe is full of mysteries waiting to be unraveled. Next, we'll take a closer look at our own galaxy's halo and the ongoing efforts to map its hidden structure. Now, let's turn our attention closer to home, to the galactic halo that surrounds our very own Milky Way. This vast, invisible sphere of dark matter stretches far beyond the bright disk of stars and gas that we typically associate with our galaxy. In fact, the Milky Way's halo is thought to extend hundreds of thousands of light years into space, enveloping the entire galaxy in a gravitational embrace. But what exactly makes up this mysterious halo, and how do we even begin to study something we can't see? The Milky Way's halo is believed to be composed primarily of dark matter, with only trace amounts of ordinary matter scattered throughout. This ordinary matter includes hot gas, faint stars, and even the remnants of ancient dwarf galaxies that were absorbed by the Milky Way long ago. While these visible components are fascinating, they make up only a tiny fraction of the halo's total mass. The real story lies in the dark matter, which makes up the overwhelming majority of the halo's structure and holds the key to understanding its true nature. Mapping the Milky Way's halo is no small feat. Scientists rely on a combination of techniques, from studying the motions of stars and gas within the galaxy to analyzing the effects of gravitational lensing caused by the halo itself. One groundbreaking method involves observing the orbits of globular clusters, dense groups of ancient stars that orbit the Milky Way. By tracking their movements, astronomers can infer the distribution of dark matter in the halo and estimate its total mass. Recent studies suggest that the Milky Way's halo could contain as much as 1 trillion times the mass of our Sun, a staggering figure that underscores the sheer scale of this invisible structure. But the halo isn't just a static shell. It's a dynamic, ever-changing part of our galaxy. For example, recent observations have revealed streams of stars and gas being pulled into the Milky Way from smaller galaxies, leaving behind trails that trace the halo's gravitational influence. These streams act like cosmic breadcrumbs, helping scientists piece together the history of our galaxy and its interactions with its neighbors. They also provide clues about the halo's shape and density, which are crucial for refining our models of dark matter. Despite these advances, many questions remain. For instance, why does the Milky Way's halo appear to be slightly lopsided? Some theories suggest that this asymmetry could be the result of past collisions with other galaxies, while others propose that it's a natural consequence of the way dark matter clumps together. Another mystery is the halo's temperature. While most of the dark matter is thought to be cold, meaning it moves relatively slowly, there's evidence that some regions might contain warm, dark matter, moving at higher speeds. Understanding these variations could help us uncover the true nature of dark matter particles. As we continue to explore the Milky Way's halo, each discovery brings us closer to solving these cosmic puzzles. From the faint glow of ancient stars to the invisible pull of dark matter, the halo is a testament to the complexity and beauty of our galaxy. And as we peer deeper into its secrets, we're reminded that even our own cosmic backyard holds mysteries that challenge our understanding of the universe. Next, we'll explore how these halos connect galaxies across the cosmos, forming bridges that shape the large-scale structure of the universe. Now, let's take a step back and look at the bigger picture. Galactic halos aren't just isolated structures surrounding individual galaxies. They play a crucial role in connecting galaxies across the vast expanse of the universe. These halos, made up mostly of dark matter, act like invisible bridges, linking galaxies together and shaping the way they interact, collide, and even merge over billions of years. One of the most fascinating examples of this can be seen in the interactions between the Milky Way and its closest neighbor, the Andromeda galaxy. Both galaxies are surrounded by massive halos of dark matter, and as they slowly move toward each other, their halos are already beginning to overlap. This invisible connection is pulling the two galaxies closer, setting the stage for a cosmic collision that will occur in about 4 billion years. When this happens, the halos will merge long before the stars and gas in the galaxies themselves collide, creating a new, larger halo that will envelop the combined galaxy. But it's not just the Milky Way and Andromeda that are connected in this way. Across the universe, we've observed countless examples of galaxies interacting through their halos. Take, for instance, the antennae galaxies, a pair of spiral galaxies in the process of merging. Observations show that their dark matter halos have already intertwined, creating a gravitational framework that guides the collision of their visible components. This interaction has triggered bursts of star formation, reshaping the galaxies into a single, chaotic structure. These intergalactic bridges don't just influence collisions, they also play a role in the formation of galaxy clusters, some of the largest structures in the universe. In clusters like the Coma cluster, hundreds or even thousands of galaxies are bound together by a vast, interconnected web of dark matter halos. These halos act like cosmic glue, holding the cluster together and influencing the motion of galaxies within it. Without these invisible connections, galaxies would drift apart, and the large-scale structure of the universe would look very different. What's truly remarkable is how these halos shape the evolution of galaxies over time. When galaxies collide, their halos don't just merge, they redistribute dark matter, creating new gravitational forces that can trigger star formation, fuel supermassive black holes, and even strip gas and stars from smaller galaxies. This process, known as tidal stripping, leaves behind trails of stars and gas that trace the paths of these interactions, offering clues about the history of galaxy formation. As we continue to study these intergalactic bridges, we're uncovering more about the role dark matter plays in shaping the universe. From the smallest dwarf galaxies to the largest clusters, these invisible connections are a testament to the intricate and dynamic nature of the cosmos. Next, we'll explore how the galactic halo and dark matter contribute to the accelerating expansion of the universe, and what this means for the fate of everything we see. Now, let's shift our gaze to an even grander scale, the role of the galactic halo and dark matter in the accelerating expansion of the universe itself. While we've seen how these halos connect galaxies and shape their interactions, their influence extends far beyond, playing a pivotal role in the very fabric of cosmic evolution. Dark matter, though invisible, exerts a gravitational pull that not only holds galaxies together, but also influences the large-scale structure of the universe. But here's where it gets even more intriguing. Dark matter's gravitational effects are intertwined with another mysterious force, a dark energy. While dark matter pulls matter together, dark energy pushes the universe apart, driving its accelerated expansion. Together, these two forces shape the destiny of the cosmos. The galactic halo, as a reservoir of dark matter, contributes to this cosmic tug of war. On one hand, its gravitational pull helps form and stabilize galaxies, clusters, and the cosmic web. On the other hand, as the universe expands, the distribution of dark matter in these halos influences how galaxies move and how structures evolve over time. This delicate balance between dark matter's gravity and dark energy's repulsion determines the rate at which the universe grows. What does this mean for the fate of the cosmos? If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate. Over billions of years, galaxies will drift farther apart, their halos stretching into the void. Eventually, even the closest galaxies will be so distant that their light will no longer reach us, leaving the night sky eerily empty. This scenario, known as the Big Freeze, paints a picture of a cold, dark universe where star formation ceases and galaxies fade into isolation. But the story doesn't end there. Some theories suggest that dark energy's influence might change over time, potentially leading to other outcomes, such as a Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. While these scenarios are speculative, they highlight the profound impact of dark matter and dark energy on the universe's ultimate fate. As we continue to study the galactic halo and its role in cosmic expansion, we're not just uncovering the secrets of dark matter, we're piecing together the story of the universe itself. From the smallest particles to the largest structures, these invisible forces shape everything we see and everything we are. Next, we'll delve into the cosmic web, a vast network of dark matter filaments that connects galaxies across the universe, revealing yet another layer of this intricate cosmic tapestry. Now, let's zoom out even further and explore the cosmic web, a breathtaking structure that stretches across the entire universe. Imagine a vast, intricate network of threads weaving through the cosmos like an invisible spider's web. These threads are made of dark matter, forming filaments that connect galaxies, clusters, and even superclusters. This cosmic web is the backbone of the universe, shaping its large-scale structure and guiding the movement of galaxies over billions of years. At the heart of this web lies the galactic halo, a dense sphere of dark matter that surrounds galaxies like our Milky Way. But the halo isn't just a standalone feature, it's a crucial node in this vast network. The dark matter within the halo extends outward, merging with the filaments of the cosmic web, creating pathways that link galaxies across unimaginable distances. These filaments act like cosmic highways, channeling gas, dust, and even entire galaxies along their lengths, fueling the growth of structures throughout the universe. What makes the cosmic web so fascinating is how it reveals the hidden influence of dark matter. While we can't see the web directly, its presence is felt through the gravitational pull it exerts on visible matter. Galaxies and clusters tend to form at the intersections of these filaments, where the density of dark matter is highest. These intersections are like bustling cosmic cities, teeming with activity as galaxies collide, merge, and evolve. The galactic halo plays a key role in this process. As a reservoir of dark matter, it not only anchors galaxies, but also connects them to the broader web. The halo's gravitational pull draws in gas and dust from the surrounding filaments, providing the raw materials needed for star formation and galaxy growth. Over time, this interplay between the halo and the cosmic web shapes the evolution of galaxies, influencing everything from their size to their structure. But the cosmic web isn't just a static framework, it's dynamic and ever-changing. As the universe expands, the filaments stretch and shift, altering the pathways that connect galaxies. This constant motion creates a delicate balance between the gravitational pull of dark matter and the repulsive force of dark energy, driving the ongoing evolution of the cosmos. By studying the cosmic web and the role of the galactic halo within it, we gain a deeper understanding of how the universe is structured and how it evolves over time. This invisible network is a testament to the profound influence of dark matter, shaping not just individual galaxies, but the entire universe. Next, we'll explore how this understanding challenges our current theories and opens the door to new possibilities in our quest to unravel the mysteries of the cosmos. Now, let's take a step into the realm of possibilities and explore the theories that go beyond what we currently know. While the standard model of physics has been incredibly successful in explaining much of the universe, it doesn't fully account for dark matter. This has led scientists to propose alternative theories, each offering a unique perspective on the nature of the galactic halo and its mysterious contents. One intriguing idea is modified gravity. Instead of invoking dark matter, this theory suggests that our understanding of gravity might be incomplete. Perhaps on cosmic scales, gravity behaves differently than we've observed in smaller systems. Proponents of this theory argue that the effects we attribute to dark matter could instead be the result of gravity operating under new rules. While this idea challenges the conventional view, it raises fascinating questions about the fundamental forces shaping the universe. Another compelling theory involves exotic particles. These are hypothetical particles that don't fit into the standard model, but could explain dark matter's elusive nature. Candidates like axions or sterile neutrinos are thought to interact so weakly with ordinary matter that they've remained undetected until now. Experiments around the world are searching for these particles, hoping to catch a glimpse of their existence. If discovered, they could revolutionize our understanding of the galactic halo and its role in the cosmos. Some theories even suggest that dark matter might not be made of particles at all. Instead, it could be a manifestation of quantum fields or other phenomena we've yet to comprehend. These ideas push the boundaries of physics, challenging us to rethink what we know about matter, energy, and the forces that govern the universe. Each of these theories offers a different lens through which to view the galactic halo. Whether it's through modified gravity, exotic particles, or entirely new concepts, they all share one thing in common. They challenge us to think beyond the standard model. As we continue to explore these ideas, we may uncover clues that reshape our understanding of dark matter and its role in the universe. This journey into the unknown reminds us that science is a process of discovery, filled with questions that lead to even more questions. As we delve deeper into these theories, we'll see how they not only challenge our understanding of the galactic halo, but also open the door to new possibilities in our quest to unravel the mysteries of the cosmos. Next, we'll explore how these theories might help us detect dark matter in ways we've never imagined. Now, let's shift our focus to a fascinating possibility that could shed light on the elusive nature of dark matter, the idea of dark matter annihilation. Imagine, for a moment, that dark matter particles aren't just passively floating through the universe. What if, under certain conditions, they collide and annihilate each other, releasing energy in the process? This phenomenon could produce detectable signals, such as gamma rays, offering us a rare glimpse into the hidden world of dark matter. The concept of dark matter annihilation hinges on the idea that dark matter particles might be their own antiparticles. When two such particles meet, they could destroy each other, converting their mass into energy. This energy might manifest as gamma rays, which are high-energy photons that we can detect with specialized instruments. If we were to observe an excess of gamma rays in regions where dark matter is thought to be concentrated, it could be a strong indicator of this annihilation process at work. However, detecting these signals is no easy task. One of the biggest challenges lies in distinguishing gamma rays produced by dark matter annihilation from those generated by other astrophysical sources, such as pulsars or black holes. The universe is filled with gamma rays from various processes, making it difficult to isolate the specific signature of dark matter. Scientists must carefully analyze the energy spectrum and spatial distribution of gamma rays to identify any anomalies that could point to dark matter. Another hurdle is the sheer faintness of the signals. Even if dark matter annihilation is occurring, the resulting gamma rays might be incredibly weak, buried under the noise of other cosmic emissions. To overcome this, researchers rely on highly sensitive telescopes, like the Fermi Gamma Ray Space Telescope, which scans the sky for gamma ray sources. By focusing on regions with high concentrations of dark matter, such as the centers of galaxies or dwarf galaxies, they hope to catch a faint but telling signal. Despite these challenges, the search for dark matter annihilation remains a promising avenue of research. If successful, it could provide direct evidence of dark matter's existence and help us understand its properties. Moreover, it would open up new ways to study the galactic halo and its role in the cosmos. As we continue to refine our techniques and instruments, we move closer to uncovering this glimmer of light in the darkness, bringing us one step closer to solving the mystery of dark matter. Next, we'll explore another intriguing aspect of the galactic halo, its temperature and how it shapes the behavior of this enigmatic structure. Now, let's turn our attention to another intriguing aspect of the galactic halo, its temperature. Unlike the fiery cores of stars or the searing heat of supernova, the galactic halo is thought to be cold, a term that might sound surprising when discussing something as vast and mysterious as dark matter. But what does it mean for the halo to be cold, and how does this shape its behavior and interactions with the visible universe? In the context of dark matter, cold doesn't refer to temperature in the way we experience it here on Earth. Instead, it describes the speed at which dark matter particles move. Cold dark matter particles are slow-moving compared to the speed of light, which means they clump together more easily under the influence of gravity. This slow, steady movement allows them to form the large-scale structures we see in the universe, such as galaxies and galaxy clusters. Without this cold property, the universe as we know it might look very different. The cold nature of the galactic halo has profound implications for how it interacts with visible matter. Because dark matter particles move so slowly, they don't collide with each other or with ordinary matter in the same way that atoms do. Instead, they pass right through, exerting their influence only through gravity. This is why the halo remains invisible, even as it shapes the motion of stars and galaxies within its grasp. The coldness of dark matter ensures that it stays diffuse and spread out, forming a vast spherical cloud around galaxies like our Milky Way. But why does this matter? The coldness of the galactic halo plays a crucial role in the formation and evolution of galaxies. In the early universe, small fluctuations in the density of dark matter acted as seeds for the growth of galaxies. These fluctuations grew over time, pulling in gas and dust to form stars and planets. Without the cold, slow-moving nature of dark matter, these structures might never have formed, leaving the universe a much emptier place. Interestingly, the coldness of the halo also affects how we study it. Because dark matter doesn't emit or absorb light, we can't observe it directly. Instead, we rely on its gravitational effects on visible matter, such as the way it bends light from distant galaxies, a phenomenon known as gravitational lensing. The cold, slow-moving nature of dark matter makes these effects more predictable, allowing scientists to map the halo's distribution and infer its properties. As we continue to explore the mysteries of the galactic halo, its cold nature remains a key piece of the puzzle. It shapes the universe on the largest scales, influencing everything from the formation of galaxies to the motion of stars. Yet, despite its importance, much about this cold, invisible structure remains unknown. What causes dark matter to be so cold? How does it interact with other forces in the universe? These are questions that drive scientists to keep searching, pushing the boundaries of our understanding. Next, we'll delve into the fascinating relationship between dark matter and black holes, exploring how these cosmic giants dance together in the vast expanse of space. Now, let's shift our gaze to one of the most fascinating cosmic partnerships, the intricate relationship between dark matter and black holes. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational powerhouse that shapes its surroundings in profound ways. But what role does the galactic halo, with its vast reservoir of dark matter, play in this cosmic dance? Supermassive black holes and dark matter are deeply intertwined, each influencing the other in ways that shape the evolution of galaxies. The dark matter in the galactic halo provides the gravitational scaffolding that helps funnel gas and dust toward the center of a galaxy, where the black hole resides. This inflow of material feeds the black hole, allowing it to grow and, in some cases, become active, emitting intense radiation that can be seen across the universe. Without the gravitational pull of dark matter, this process would be far less efficient, and black holes might not grow to the immense sizes we observe today. But the relationship isn't one-sided. As black holes grow and consume matter, they release enormous amounts of energy in the form of jets and radiation. These outbursts can heat up the surrounding gas, pushing it away and temporarily halting the flow of material into the black hole. This feedback mechanism, driven by the black hole's activity, can also affect the distribution of dark matter in the galactic halo. Over time, the interplay between the black hole and the halo helps regulate the growth of both, creating a delicate balance that shapes the galaxy's structure and evolution. One of the most intriguing aspects of this relationship is how dark matter behaves near a black hole. While dark matter doesn't interact with light or ordinary matter in the same way, its gravitational influence is undeniable. Near a black hole, the intense gravitational field can cause dark matter particles to accumulate, forming a dense spike around the black hole. This spike can enhance the black hole's gravitational pull, further influencing the motion of stars and gas in the galaxy's core. In some cases, this concentration of dark matter might even affect the black hole's spin or the way it interacts with its surroundings. The dance between dark matter and black holes also has implications for the larger universe. As galaxies collide and merge, their central black holes can come together, creating even more massive black holes. During these mergers, the dark matter halos of the galaxies also combine, redistributing and reshaping the gravitational landscape. These events can trigger bursts of star formation and influence the growth of the new galaxy that emerges from the collision. In this way, the partnership between dark matter and black holes plays a key role in the cosmic story, shaping the universe on both small and large scales. Yet, despite our growing understanding, many questions remain. How exactly do dark matter and black holes influence each other over billions of years? Could dark matter particles be captured or destroyed by black holes, or do they simply orbit in the halo, unaffected? These mysteries continue to drive research as scientists use simulations and observations to unravel the secrets of this cosmic dance. As we explore this dynamic relationship, we gain a deeper appreciation for the interconnectedness of the universe. From the invisible pull of dark matter to the immense gravity of black holes, these forces work together to shape the cosmos in ways we are only beginning to understand. Next, we'll turn our attention to another intriguing question. Where does the galactic halo end, and how do scientists define its boundaries? Now, let's venture into one of the most puzzling questions about the galactic halo. Where does it actually end? Unlike the sharp edges of a planet or the defined boundaries of a star, the galactic halo doesn't have a clear-cut edge. Instead, it fades gradually into the vast emptiness of intergalactic space, making it incredibly challenging for scientists to determine its exact limits. To understand this, imagine standing on a beach, watching the waves roll in. The water doesn't stop abruptly. It thins out as it reaches the shore, blending seamlessly with the sand. The galactic halo behaves in a similar way. Its dark matter particles become less dense as you move outward from the galaxy's center, eventually merging with the sparse dark matter that fills the space between galaxies. This gradual thinning makes it difficult to pinpoint where the halo truly ends. So, how do scientists estimate the size and mass of something so elusive? One method involves studying the motion of stars and gas on the outskirts of galaxies. These objects are influenced by the gravitational pull of the dark matter in the halo, even at great distances. By measuring how fast these stars and gas clouds move, astronomers can calculate the amount of dark matter needed to keep them in orbit. This gives them a rough idea of the halo's mass and how far its gravitational influence extends. Another approach relies on gravitational lensing, a phenomenon where the gravity of dark matter bends the light from distant objects. By observing how light is distorted around galaxies, scientists can map the distribution of dark matter in the halo and estimate its outer limits. These observations often reveal that the halo extends much farther than the visible parts of a galaxy, sometimes reaching hundreds of thousands of light years beyond its stars and gas. But even with these tools, defining the edge of the galactic halo remains a challenge. Unlike ordinary matter, dark matter doesn't emit light or interact with electromagnetic forces, so it leaves no direct trace for us to observe. Instead, scientists must rely on indirect methods and sophisticated models to piece together its structure. These models suggest that the halo's boundary isn't fixed. It can change over time as galaxies interact, merge, or grow. One fascinating aspect of this research is the discovery that the galactic halo might not be perfectly spherical. While it's often depicted as a smooth, round shell, simulations show that it could have a more irregular shape, with clumps and streams of dark matter extending far beyond the galaxy's visible disk. These features add another layer of complexity to understanding where the halo ends and intergalactic space begins. As we continue to explore the edges of the galactic halo, we're reminded of just how much there is still to learn about the universe. The boundaries of this mysterious structure remain elusive, but each discovery brings us closer to understanding its true nature. Next, we'll delve into another intriguing aspect of dark matter, how its presence affects the flow of time itself, adding yet another dimension to this cosmic mystery. Now, let's turn our attention to a mind-bending aspect of the galactic halo, its influence on the very fabric of time. According to Einstein's theory of relativity, massive objects like galaxies and their dark matter halos don't just warp space, they also warp time. This means that the presence of the galactic halo doesn't just shape the universe around it, it also alters how time flows within its gravitational grip. To understand this, picture time as a river. In most places, the river flows smoothly and evenly, just as time ticks by at a steady pace here on Earth. But near a massive object like the galactic halo, the river's flow changes. The immense gravitational pull of the halo's dark matter creates a kind of time warp, where time moves slower compared to regions with less gravity. This effect, known as gravitational time dilation, is a direct consequence of Einstein's theory. Imagine two clocks, one placed deep within the galactic halo, where dark matter is densest, and another far away in empty space. Over time, the clock in the halo would tick more slowly than the one in empty space. This isn't just a theoretical idea. It's been confirmed by experiments here on Earth and observations of distant cosmic phenomena. For example, satellites in orbit around our planet experience time slightly faster than we do on the surface because they're farther from Earth's gravitational pull. The same principle applies to the galactic halo, but on a much grander scale. The implications of this are profound. If you could somehow stand at the edge of the galactic halo, you'd experience time differently than someone in a region with less dark matter. Over billions of years, this difference could add up, creating a kind of cosmic clock that ticks at varying rates across the universe. This phenomenon isn't just a curiosity, it's a crucial part of how we understand the universe's structure and evolution. But the story doesn't end there. The galactic halo's influence on time also plays a role in the large-scale behavior of the cosmos. For instance, as galaxies move and interact, their dark matter halos can create ripples in space-time, subtly altering the flow of time in their vicinity. These ripples, combined with the halo's gravitational pull, can affect how galaxies form, merge, and evolve over billions of years. As we explore this connection between dark matter and time, we're reminded of how deeply intertwined the universe's mysteries are. The galactic halo isn't just a silent, invisible presence. It's a dynamic force that shapes not only space, but also the very passage of time. Next, we'll uncover how this mysterious structure has played a pivotal role in the evolution of the cosmos, from the Big Bang to the galaxies we see today. Now, let's take a step back and consider the bigger picture, the galactic halo's role in the grand story of cosmic evolution. From the earliest moments after the Big Bang to the galaxies we see today, this invisible sphere of dark matter has been a silent architect, shaping the universe in ways we're only beginning to understand. In the aftermath of the Big Bang, the universe was a swirling sea of particles and energy. As it expanded and cooled, tiny fluctuations in density began to form. These fluctuations were the seeds of future galaxies, and dark matter played a crucial role in their growth. The galactic halo, with its immense gravitational pull, acted like a cosmic scaffold, drawing ordinary matter, gas, dust, and eventually stars, into its grasp. Without this invisible framework, galaxies as we know them might never have formed. Over billions of years, these halos of dark matter grew larger and more complex, pulling in more material and giving rise to the first galaxies. As galaxies formed, their dark matter halos continued to influence their evolution. The gravitational pull of the halo shaped the distribution of stars and gas within the galaxy, determining its structure and even its fate. For example, when galaxies collide, their dark matter halos interact, often merging to form even larger structures. These cosmic mergers are some of the most dramatic events in the universe, and they wouldn't be possible without the guiding hand of dark matter. But the galactic halo's influence doesn't stop there. It also plays a key role in the formation of galaxy clusters, the largest structures in the universe. These clusters are held together by the combined gravitational pull of their dark matter halos, which act like cosmic glue, binding hundreds or even thousands of galaxies into a single, massive entity. Without dark matter, these clusters would simply fly apart, and the universe would look very different. Even today, the galactic halo continues to shape the cosmos. As galaxies spin and stars are born and die, the halo's gravitational influence ensures that everything stays in balance. It's a constant, invisible presence, quietly guiding the evolution of the universe on the grandest scales. And while we can't see it directly, its effects are everywhere, from the rotation of galaxies to the bending of light from distant stars. As we reflect on the galactic halo's role in cosmic evolution, we're reminded of just how much there is still to learn. This invisible structure has been a driving force in the universe's story, from its earliest moments to the present day. And as we continue to explore its mysteries, we're uncovering new insights into the nature of dark matter, the formation of galaxies, and the ultimate fate of the cosmos itself. Next, we'll delve into the biggest unanswered questions about the galactic halo and the ongoing quest to unravel its secrets. As we venture deeper into the mysteries of the galactic halo, it's impossible not to wonder about the questions that still linger in the shadows of our understanding. Despite decades of research, dark matter remains one of the most elusive puzzles in modern science. What exactly is it made of? How does it interact with the visible universe? And why does it seem to dominate the cosmos while remaining so utterly invisible to us? These are just a few of the questions that keep astronomers and physicists awake at night. One of the most pressing mysteries is the true nature of dark matter particles. While scientists have proposed candidates like weakly interacting massive particles and axions, none have been definitively detected. Experiments deep underground and in space continue to search for these elusive particles, but so far, they've remained just out of reach. What if dark matter isn't made of particles at all? Could it be something even more exotic, like a new form of energy or a flaw in our understanding of gravity itself? These possibilities challenge the very foundations of physics and keep the quest for answers alive. Another unanswered question is the exact structure and boundaries of the galactic halo. While we know it's vast and spherical, its edges are difficult to define. Does it simply fade into the void, or is there a clear boundary where its influence ends? And how does it interact with other halos in the universe? Observations suggest that halos may form bridges between galaxies, but the details of these connections remain unclear. Understanding these interactions could reveal how galaxies grow, merge, and evolve over time. Then there's the mystery of dark matter's role in the universe's expansion. We know the cosmos is growing larger at an accelerating rate, but what part does dark matter play in this process? Is it driving the expansion, or is it being shaped by it? And how does this tie into the fate of the universe? Will dark matter eventually determine whether the cosmos continues to expand forever, collapses back on itself, or meets some other unknown destiny? Perhaps the most tantalizing question of all is whether dark matter could hold the key to life itself. Could its gravitational influence have played a role in creating the conditions necessary for galaxies, stars, and planets to form? And if so, does that mean dark matter is somehow connected to the emergence of life in the universe? These questions blur the line between science and philosophy, reminding us just how much we still have to learn. The quest to unravel these mysteries is far from over. Every discovery brings new questions, and every question pushes us closer to understanding the true nature of the galactic halo and the universe it shapes. As we continue to explore, one thing is certain: the journey to uncover these secrets is as thrilling as the answers themselves. Next, we'll look at the cutting-edge missions and technologies that are helping us probe the galactic halo like never before. As we turn our gaze toward the future, the tools and missions designed to unravel the secrets of the galactic halo are nothing short of extraordinary. Among these, the James Webb Space Telescope stands as a beacon of hope. Launched in December 2021, this marvel of engineering is already transforming our understanding of the cosmos. With its unparalleled ability to peer into the infrared spectrum, the James Webb Telescope can detect the faintest traces of light from the earliest galaxies, offering clues about how dark matter shaped the universe in its infancy. By observing distant galaxies and their halos, scientists hope to map the distribution of dark matter with unprecedented precision, shedding light on its role in cosmic evolution. Another groundbreaking mission on the horizon is the Euclid spacecraft, set to launch in the coming years. Designed by the European Space Agency, Euclid aims to create a three-dimensional map of the universe, focusing on the large-scale structures shaped by dark matter. By measuring the subtle distortions of light caused by gravitational lensing, Euclid will provide a clearer picture of how dark matter is distributed across the cosmos. This mission could help answer some of the most pressing questions about the galactic halo, such as its boundaries and how it interacts with other halos in the universe. Closer to home, the Vera C. Rubin Observatory in Chile is preparing to revolutionize our understanding of the night sky. Equipped with the largest digital camera ever built, this observatory will conduct a 10-year survey of the southern sky, capturing detailed images of billions of galaxies. By analyzing these images, scientists hope to uncover the invisible threads of dark matter that connect galaxies and shape the cosmic web. The data collected could also reveal how dark matter influences the formation and evolution of galaxies, including our own Milky Way. Meanwhile, underground experiments continue to push the boundaries of what we know. Facilities like the Large Hadron Collider and the Deep Underground Neutrino Experiment are searching for dark matter particles by recreating the extreme conditions of the early universe. These experiments aim to detect the faintest signals of dark matter interactions, offering a glimpse into the fundamental nature of this mysterious substance. While no definitive detection has been made yet, each experiment brings us closer to understanding the particles that make up the galactic halo. As these missions and technologies come online, they promise to transform our understanding of the galactic halo and the universe at large. Each discovery will bring new questions, and each question will push us further into the unknown. The journey to uncover the secrets of dark matter is far from over, but with these cutting-edge tools, we are closer than ever to unlocking the mysteries of the cosmos. Next, we'll explore how the galactic halo and dark matter might be connected to the emergence of life in the universe, a question that blurs the line between science and philosophy. Now, let's venture into a fascinating question that bridges the realms of science and philosophy. Could dark matter and the galactic halo hold the key to the emergence of life in the universe? While dark matter itself remains invisible and elusive, its gravitational influence has shaped the cosmos in ways that may have made life possible. Without the galactic halo, galaxies like our Milky Way might never have formed, and without galaxies, the stars and planets that nurture life might not exist. Consider this: the gravitational pull of dark matter in the galactic halo played a crucial role in gathering ordinary matter into dense clouds, which eventually collapsed to form stars and planets. These cosmic nurseries, scattered across galaxies, became the birthplaces of solar systems like our own. Without the stabilizing presence of dark matter, galaxies might have been too chaotic or unstable to support the long-term conditions necessary for life to emerge. In this way, the galactic halo may have indirectly set the stage for the development of habitable worlds, but the connection doesn't end there. Dark matter's influence extends to the very structure of the universe. By shaping the cosmic web, a vast network of filaments connecting galaxies' dark matter has created the scaffolding upon which galaxies and galaxy clusters are built. This intricate web not only determines where galaxies form, but also influences their interactions and evolution over billions of years. In regions where dark matter is denser, galaxies are more likely to collide and merge, triggering bursts of star formation that could lead to the creation of new planets. These dynamic processes may have played a role in creating the conditions for life to arise in certain corners of the universe. Could dark matter also have a more direct impact on life itself? While this remains speculative, some scientists have proposed that dark matter particles might interact with ordinary matter in subtle ways, potentially influencing biological processes. For example, if dark matter particles occasionally collide with atoms in living organisms, they could trigger rare but significant changes at the molecular level. Though this idea is still in its infancy, it opens up intriguing possibilities for understanding how the unseen forces of the universe might shape life in ways we are only beginning to imagine. As we ponder these questions, it's worth reflecting on how the galactic halo and dark matter have shaped not just the universe, but our own existence. The same mysterious substance that holds galaxies together may have also created the conditions for life to flourish. This cosmic connection reminds us that the story of life is deeply intertwined with the story of the universe itself. Next, we'll explore how the galactic halo and dark matter have captured the imagination of storytellers, inspiring tales that blend science with fiction. Now, let's step into a realm where science meets storytelling, where the mysteries of the galactic halo and dark matter have inspired countless tales of wonder and imagination. From the silver screen to the pages of novels, the enigmatic nature of dark matter has captured the creative minds of writers, filmmakers, and artists, transforming complex scientific concepts into captivating narratives that resonate with audiences worldwide. In science fiction, the galactic halo often serves as a backdrop for epic adventures, a vast and mysterious expanse that challenges the limits of human exploration. Films like Interstellar and Contact have woven dark matter into their plots, using it as a driving force behind interstellar travel or as a key to unlocking the secrets of the universe. These stories, while fictional, often draw on real scientific theories, blending fact with fantasy to create a sense of awe and possibility. They invite us to imagine what might lie beyond our current understanding, sparking curiosity about the unseen forces that shape our cosmos. Books, too, have embraced the allure of dark matter and the galactic halo. Authors like Isaac Asimov and Arthur C. Clarke have explored the implications of these cosmic mysteries, crafting stories that delve into the profound questions they raise. In their works, dark matter becomes more than just a scientific concept. It becomes a symbol of the unknown, a reminder of how much we have yet to discover. These narratives often challenge us to think beyond the boundaries of our knowledge, encouraging us to ponder the deeper mysteries of existence. Even in video games and graphic novels, the galactic halo has found a place as a source of intrigue and inspiration. Games like Mass Effect and Destiny feature dark matter as a central element of their lore, creating immersive worlds where players can explore the consequences of its influence. These interactive experiences allow us to engage with the concept of dark matter in a hands-on way, blending entertainment with education and sparking interest in the science behind the fiction. What makes these portrayals so compelling is their ability to take something as abstract as dark matter and make it tangible, relatable, and even thrilling. By weaving it into stories of adventure, discovery, and human ingenuity, popular culture helps us connect with the mysteries of the universe on a personal level. It reminds us that science and imagination are not opposites, but partners in our quest to understand the cosmos. As we reflect on these creative interpretations, it's clear that the galactic halo and dark matter have become more than just scientific phenomena. They are symbols of the unknown, gateways to endless possibilities. They challenge us to dream, to explore, and to question what lies beyond the limits of our knowledge. And as we continue to uncover the secrets of the universe, these stories will remain a testament to the enduring power of curiosity and imagination. Next, we'll turn our gaze inward, reflecting on what the galactic halo and dark matter mean for our place in the cosmos. As we journey through the vastness of the cosmos, the galactic halo and dark matter invite us to pause and reflect on our place in the universe. These invisible forces, though hidden from our eyes, shape the very fabric of reality, influencing the formation of galaxies, the motion of stars, and the destiny of the cosmos itself. They remind us that what we see is only a fraction of what exists, and that the universe is far more complex and mysterious than we can fully comprehend. Consider this: every galaxy, including our own Milky Way, is cradled within a vast sphere of dark matter, a cosmic embrace that holds everything together. Without it, the stars we gaze upon at night might never have formed, and the universe as we know it would be unrecognizable. This realization humbles us, reminding us of how interconnected we are with the cosmos. The atoms in our bodies, the light from distant stars, and the gravitational pull of the galactic halo all share a common origin, tracing back to the Big Bang and the birth of the universe. Yet, for all we've learned, the galactic halo and dark matter remain shrouded in mystery. They challenge us to confront the limits of our knowledge and to embrace the unknown with curiosity and wonder. What lies beyond the edges of the halo? What secrets does dark matter hold about the nature of reality? These questions are not just scientific inquiries. They are invitations to explore the deeper meaning of our existence. In a universe filled with billions of galaxies, each containing billions of stars. It's easy to feel small, but the story of the galactic halo and dark matter tells us something profound. Even the unseen and the unknown play a vital role in the grand tapestry of existence. We are part of something far greater than ourselves, a cosmic dance that has been unfolding for billions of years and will continue long after we are gone. So, as we ponder the mysteries of the galactic halo and dark matter, let's also reflect on our own place in this vast universe. What does it mean to be a tiny speck in an infinite cosmos? How does this perspective shape our understanding of life, purpose, and connection? These are questions that science alone cannot answer, but they are questions worth asking, for they remind us of the beauty and mystery of existence. As we close this chapter of our cosmic journey, let's carry this sense of wonder with us. The galactic halo and dark matter are not just scientific phenomena, they are windows into the infinite, reminders that the universe is full of surprises waiting to be discovered. And perhaps, in seeking to understand them, we come to understand a little more about ourselves. As we reach the end of our journey through the mysteries of the galactic halo and dark matter, let's take a moment to reflect on what we've uncovered. We've explored how this invisible sphere of dark matter cradles galaxies like our Milky Way, shaping their formation and guiding their motion through the cosmos. We've delved into the challenges scientists face in studying something they cannot see, yet whose presence is felt in every corner of the universe. And we've pondered the profound questions these mysteries raise about our place in the grand scheme of existence. The galactic halo and dark matter remind us that the universe is far more than what meets the eye. They challenge us to look beyond the visible, to question what we think we know, and to embrace the unknown with curiosity and wonder. These cosmic enigmas are not just scientific puzzles, they are invitations to explore, to imagine, and to connect with the infinite. But the story doesn't end here. The mysteries of the galactic halo and dark matter are far from solved. Every discovery leads to new questions, and every question brings us closer to understanding the universe and ourselves. So, as we close this chapter, I invite you to keep exploring. Look up at the night sky and wonder about the unseen forces at work. Dive into the latest research, or simply let your imagination wander among the stars. The cosmos is vast, and its secrets are waiting for curious minds like yours to uncover them. If this journey through the galactic halo and dark matter has sparked your curiosity, don't stop here. Share your thoughts in the comments below. What fascinates you most about these cosmic mysteries? And if you're eager to learn more, hit that subscribe button and join us as we continue to explore the wonders of the universe. Together, let's keep reaching for the stars, one mystery at a time. As we stand at the edge of understanding, gazing into the vast expanse of the cosmos, it's impossible not to feel a profound sense of awe. The galactic halo, this invisible sphere of dark matter, is more than just a scientific mystery. It's a testament to the boundless wonders that lie beyond our comprehension. It whispers to us of a universe that is far grander, far stranger, and far more beautiful than we could ever imagine. Think of it like this: the galactic halo is the unseen hand that shapes the dance of galaxies, the silent force that holds the stars in their celestial embrace. It's a reminder that even in the darkness, there is structure, purpose, and beauty waiting to be discovered. And while we may not yet fully understand its secrets, the very act of seeking answers connects us to something greater, a shared human curiosity that spans generations and cultures. So, as we close this chapter, let's carry that sense of wonder with us. Let's look up at the night sky and marvel at the mysteries it holds. Let's celebrate the questions as much as the answers, for it is in the unknown that we find the spark of discovery. The Galactic Halo is not just a scientific puzzle. It's an invitation to dream, to explore, and to imagine what lies beyond the limits of our understanding. Thank you for joining me on this journey through the mysteries of the universe. If this exploration has ignited your curiosity, don't let it end here. Share your thoughts in the comments below. What part of this cosmic mystery fascinates you the most? And if you're eager to dive deeper into the wonders of the cosmos, hit that subscribe button and join us as we continue to unravel the secrets of the universe. Together, let's keep reaching for the stars, one question at a time. Until next time, keep wondering, keep exploring, and keep looking up. The universe is waiting. you.